Go.
Okay. Welcome back. So this is the fourth physics lesson. So this should be the last one, and we should be able to run through things decently quickly, but we'll try the best to stay on schedule. And if we don't finish, we'll take out some of the bio lessons because I don't think bio is that long as we planned it. So let's just jump straight into it. So last week we were learning kinematics, right? Which is different because now we're going to be dealing with dynamics. So in dynamics, it focuses on forces and applications of that, but kinematics focuses on things like speed, distance, and time. So we're going to be moving to a different realm of things. Yeah, but it shouldn't be that much of a change. Okay, so okay, so this is the so Newton's laws of motion. So you may have heard of the story of Isaac Newton. So he was sitting. Wow, this is such a horrible picture. But he was sitting on the ground, and then there was a tree, and the apple fell onto him, and then he discovered gravity. Like it made him think. So he actually discovered a lot of other things. Right? He's like I would say people would call him the founding father of physics, but that does make sense because let me move my. Wait, what screen are you looking at right now? Are you still looking at the physics lesson?
Yeah.
Okay, I was just checking. Okay, anyway, so people would consider him the founding father of physics because he developed most of these ideas and how we look at objects and how they interact every day. So if you want someone to blame for your physics unit, you can just blame him. And I think he invented calculus as well. So yeah, he's done a lot of things. So Newton's laws of motions, laws of motion. So these are laws. So these are like these are recorded, these are observations, right? That Newton recorded and he determined that these are always true. So all of these laws are true. So it's different. A law is different from a theory because a theory is something you can always improve on. Your theory is your best explanation of things, but your laws are a set of recorded observations, so they're always true. So let's just look at these laws of motion. So Newton's first law of motion, which will like Newton's blank law will be written as N number L. Okay, so Newton's first law is that an object remains at rest or in uniform motion. I don't know why I have this, unless an unbalanced force acts upon it. This property is known as inertia. So this is called the law of inertia. So what does that actually mean? Okay, so what that means is if you have like an object, so let's say a ball is rolling, okay? It's just rolling by itself at a constant speed, 5 meters per second. Theoretically, the ball should never stop moving, okay? But you're probably asking, well, the ball does stop moving, okay? Like, uh, let's say you drop it on your driveway and now it's rolling to your grass, okay? But so, then the ball stops at the grass. So why does the ball stop at the grass if Newton, right, discovered that it does not move? Well, that's because there's an unbalanced force that acts upon it. So the force that acts upon the ball when it stops, right, is friction. So FF, right? So friction is a force that opposes motion. It's a force that is caused by the interaction of two surfaces. So like the ball on the grass is two surfaces and they're interacting. And then in nature there's a force that because of the interaction of the two surfaces, because the molecules are interacting, there's a force that opposes that motion that that directs your speed of the ball to be like slower. Okay, but we'll understand why it's slower. But just keep a note that the reason why you don't see like things go on forever is because there always is an unbalanced force, and this force is called friction. Okay. Okay. So Well, so the next law actually helps. Okay, wait, let's talk about this law a little bit more. Okay, so so this helps. So to visualize why this law is true, you have to think about multiple real life examples. So, for example, right, uh, when you're sitting in the car, when you're sitting in your car and the brakes is slammed really, really hard, your body in the seat propels forward, right? It like it shifts forward, and you have a seatbelt, so you won't get hurt. Okay, so does why does uh why do you just suddenly like lunge forward when the car stop when the brakes are slammed so the car stops? Okay, so well, you may not feel like this, but you are moving at the same speed as the car. Okay, so you are moving at the same speed as a car. So you are right now in like an ideal state of like motion, I guess. Like you're just in an ideal state because you're moving at a constant speed. So hold on, let me drink some water. You are moving. You're at you're at one of your ideal states. So so naturally the object is going to remain in the state, right? Unless an unbalanced force acts upon it. But suddenly you slam the brakes, right? That's an unbalanced force. That's a really large force, and the car stops. But you, right? You don't stop because you are moving at the same speed as the car. But if the car stops, you are technically still moving forward. So as soon as the brakes are slammed, you propel forwards because because you were in uniform motion and you were in uniform motion and you still are, but the car isn't. So if the car stops and you're still moving, well then it makes sense for you to just bounce forward because that's still the direction that you're naturally trying to go to. Okay, if that makes sense. If it doesn't make sense, just say it doesn't make sense. But another way that this law works is if you're on a ship, okay, and you're holding a ball, right? The ship is moving this way at a speed, right? So the question is, if you drop the ball, right? Uh, if it takes 1 second to drop the ball, and then 1 second you're over here, right? Does the ball land here or here? Does it land at A or does it land at B if the ball drops in 1 second and in 1 second you're here? Um, yeah, so you like tell me like this is a question that I'm asking you. So like where do you think the ball would drop to, knowing what Newton's first law is? Okay, it's gonna go downwards, obviously, but the question was, is it gonna be at point A or point B? Point A. Okay, so it's not gonna be at point A. Okay, so so in the car, in the example with the car, right? You and the car are moving at the same speed, right? So you and the car are moving at the same speed, right? And then if the car stops moving, right, because of an unbalanced force, and that force is like you slam the brakes, so then the car slows down. So then there's a force coming opposite of the way you're moving. So there's an unbalanced force, right? So the car slows down, but you are still moving at your own speed. So you still move forward. So that's why in a car, when you hit the brakes really, really fast, you like propel forwards because you're still trying to move forward because that's your ideal, your ideal state, right? State, quote unquote. This is the best way I can explain it. So that's why you move forward, but the car doesn't. So that's why you have a seatbelt, so you don't get launched to the front of the car. Okay. So in here, right, if the boat is moving and you are also moving and the ball is also like, keep in mind you guys are all moving at the same speed, right? and then you drop the ball at this specific point, right? But the problem with this is that when you drop it, the ball is still moving this way. The ball is still moving this way when you drop it here, right? So 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 it would actually drop to a different position than you originally dropped it because the ball was still moving here. So basically, there's a speed here, and there's a speed this way, and there's a speed this way, and then the speed this way does not disappear, so it will affect the travel. It will affect the motion of the ball, right? And it will basically drop to another position that is further away from where you actually dropped it because it's still moving towards that direction. So like if you add the forces together, it'll like drop like here. It'll drop because the two speeds are added up. And because it's moving, it never stop moving to the right. When it's getting dropped, but it's going right and right. It's going righter as it's getting dropped. Okay. Does that make sense? Type a yes or a no in the chat. Yeah. Okay. Um. Oh, okay. So does that make sense? Okay. So I'm gonna ask you a question on this law. Okay. So you have a circle, right? You have like a little toy, and then someone puts a coin on here, right? And I'm gonna take away the wheel. I'm gonna take away this little circle, this little like this like Hot Wheel track, and here's a coin, right? What happens to the coin when I take this away? Okay, just open your don't type it, just open your mic and just tell me.
It would like, so if you take it away, it would the coin would fall forward.
What do you mean forward?
Oh, just fall off.
Okay, what do you mean by fall off? Okay, so what I'm asking is, where does the coin go? Okay, so let me mark some places the coin was let me mark some places the coin would go. Okay, so this is where you take away the circle. Okay, so this is point A. Mm-hmm. This is point B, and this is point C. Where would the ball possibly go if you take it away? So would it be to the right? Actually, point D as well. Okay, would it go to the left to the left bottom, or the very bottom, or the direct bottom, to the right bottom, or would it stay on the wheel if you take away the wheel with the coin on it?
It would fall onto point D.
D, it would go here. Okay, can you give me a brief explanation on why you think it would go there?
It's because like, so like you're pulling the wheel backwards, right? So like the coin would just fall forward.
Okay, what are these backward forward terminologies? Like, just use like left or right or something, because like I haven't given you a perspective on like what is forward and what is backward, so just try to use like simpler terms to describe these things, okay? But this would not happen, okay? So what would actually happen is that it would fall straight down to the bottom, okay? Okay, try to think about Newton's laws when you answer this question. Okay, so Newton's law, first law, says that everything wants to stay the same, right? Unless something happens, unless an unbalanced force acts upon it, right?
Yeah.
So right now, your object is at rest, right? And it's at rest over here. So if I take away this little wheel, right? If I take it away, for a brief moment, this is still at rest. It's not moving, okay? So if I take away the wheel, it doesn't move with the wheel because it's staying at rest. It's staying in the same place. It wants to stay here. So because the object, quote unquote, wants to stay here, when you take away what's holding it, it falls straight down because it's trying to stay the same way it is. And the best way to do that is to do nothing because it's not moving, right? It wants to stay the way it is. It's not moving. So it's not going to move so it's not going to move if unless an unbalanced force acts upon it. But there's no unbalanced force that acts upon it except you're just taking away what's it's sitting on. So it's still not going to do anything because it doesn't want to, and it'll just fall to the ground because that's what happens. Things fall to the ground if they're not supported. So does that make sense?
Okay.
Okay. We'll go over this in a bit because I feel like you're a little bit confused on what's happening, but it should be fine. But we'll see. Okay, so the second law is an object will accelerate in the direction of the unbalanced force acting upon it. So write that down. So let's analyze what this said. So an object will accelerate in the direction of an unbalanced force acting upon it. So let's look at the example with the ball. Okay. Okay. So what do we know about the ball? Like, what do we know what happens between the surfaces of the ball and the ground that it's rolling on? What is what in that ball? What is the natural phenomenon that is going to happen to the ball?
It may eventually stop.
It will stop. Okay, so why will it stop? What is making it stop?
The unbalanced force.
Which is called what?
Friction.
And it occurs because like why does it happen? That's what I'm asking. It's okay to say I don't know. Hello? So if you don't know the answer, it's best to say I don't know instead of like just waiting in silence because I'm only going to respond when you respond. So keep that in mind. So do you know why friction happens?
No.
Okay, so just say I don't know next time then. So force of friction basically happens when the two surfaces of an object and the ground or whatever you're on when they interact with each other. That is what happens. That is why friction occurs. It's because it's a force that interacts between the two surfaces of things. Okay.
Okay.
This water is good. Okay, so now we know that although the object is trying to move at a constant speed, there's a force of friction acting against where it's going. Okay, so and also so now we know there's a force and we know the direction of the force. So because we know the direction of the force, what other things do we know about what things do the direction of the force tell us about something else based on this law that's sitting right in front of you?
Sorry, what was the question?
Okay. So the question was, because we know the direction of the force, what other things do we know the direction of? Okay, so this is not like a knowledge question. Like it's like you have to use this law to draw a conclusion. This is why we're learning the laws. I'm not throwing like random facts at you. So based on that law there, right? What what is the other thing that we know the direction of, if we know the direction of the force?
The direction of the object.
The direction of the object?
Oh, yeah.
Okay, read the law again. Okay, so the law says an object will accelerate in the direction of the unbalanced force. So, based on that sentence, what do we know the direction of?
In what direction is the acceleration?
Okay, that was not the question, but okay.
No, because you're asking about a force, right?
No, I'm asking like, this is what I'm asking, okay?
Okay.
I'm asking based on this like description, right? If we know the direction of the force, what is the other like quantity that we know the direction of? Hello?
So we know the direction. Here, let me. I need to understand your question now.
Oh my, okay. That's not a hard question. My question was, if we know the direction of the force, what is the other quantity, the other measurement that we also know the direction of?
So we know there's a force of friction, right? That's what you've drawn on your
Right?
image.
Yeah. So
Wouldn't
like,
you have a velocity on top of your? Is that what that?
okay, I was just trying to say that we also know the direction of the acceleration. Because Newton's second law is that an object accelerates in the direction of the unbalanced force. So whichever way the force is acting upon it is the way the acceleration is acting upon it. Does that make sense?
Okay.
Like this is what it like I'm just reiterating what this said. So this should not be like a concept that is like difficult to grasp. Like this is just you just read what this says. But like let's think about it. Okay, so now let's go back to this example. Okay, so the ball is moving to the left. So I'm gonna just call this like okay. No, I'm gonna just whatever. Okay, so the ball is moving to the left, and the acceleration is moving to the right. Okay, so what if you remember? What was the interaction? What is the relationship between the direction of acceleration versus the direction of the velocity? Do you remember this relationship?
Um.
Oh, how would we calculate acceleration from velocity?
I did not ask that.
Bro, you just asked what's the relationship between acceleration and
Yeah,
velocity.
what I asked, what is the relationship between the direction of acceleration and the direction of velocity?
That's a lot.
Okay, I'm just gonna like just speed by now, okay? Like this is I think we're off we're like off right now. But anyway, so we know that if the direction of the acceleration is the same as the direction of the velocity, we know that the object goes faster, okay? But if the direction of acceleration is not equal to the direction of velocity, so they're opposite, like the vectors are opposite, then we know that the object is getting slow. The object is getting slower. Okay. So what does getting slower mean again? So based on the charts and all that we did last week, we know that slow means speed goes to zero. So that helps explain why things slow down when they interact with the surfaces. Well, it's slowing down because there's a frictional force which accelerates an object in the opposite direction of its velocity, which slows down the object, which brings it to rest. That is basically how that is essentially the explanation for why things slow down. Like when you roll a ball on the grass, right? It slows down, and it slows down because of friction, because of the unbalanced force that is acting upon it. So the first two laws of Newton can be tied together. So it remains at rest unless an unbalanced force acts upon it. Okay. So if there is a force that acts upon it, right, it'll get faster or slower. So it's pretty obvious that when there's a force acts upon it, like let's say I push the ball, right? I push the ball, then the ball is going to get faster because the acceleration is the same direction as the force, which is the same direction as the velocity, which means it's getting faster. Okay. So now there's a formula revolved around this, right? The formula for force, right, for Newton's second law is force equals mass times acceleration, right? Where your mass is in kilograms and your acceleration is in meters per second squared, and that would make your force into newtons because Newton expanded on the knowledge of force. I think he named the unit after himself, but someone else he probably named it after himself. Come on now. But so the unit for force is Newton. And a Newton is equivalent to a kilogram times a meter over second squared. So mass times acceleration is force. Okay, so now we're going to try a problem with this. Okay, so it's not gonna be that straightforward because yeah, but the most straightforward type questions are like this: a 15,000 kilogram car accelerates at 4.4 meters per second squared. What is the force used? So in science 10, right, friction is not really considered. So you don't do a lot of calculations where there's a force that is acting on the object and then there's a force that is against the object, right? So this is like a typical, this is what happens in real life. But in science 10, we don't consider friction. We just imagine that there's this that that the object does not that the surfaces interact, but there's no force that comes between them and doesn't slow it down and affect the travel at all. Okay, so don't worry about friction because I'm not answering because the questions will never contain that. So based on this simple formula, we can easily calculate this question. So you can try this on your own, but yeah. So just try it on your own right now, and I'll just go over it real quick. So do you want to try this question on your own, or do you just want me to just doze through it and just teach it?
You can go through it.
Okay, wow, okay. So force equals mass times acceleration. We have the mass, we have the acceleration. So force equals the mass, which is 1,500 kilograms, times the acceleration, which is 4.4 meters per second squared. So the total force exerting on it is this thing combined. So it'll be 1,500 times 4.4, which is 6,600 newtons. Oh wait, I did not talk about. Oh, okay, I forgot to talk about something. So okay, I'm gonna ask you this question because you interact more. Okay, so what type of quantity is force? Is it a vector or a scalar? Is it a vector or a scalar? The break coming up.
It
Really?
is a vector quantity.
It is a vector quantity. So how do you determine it was a vector quantity?
Because like vector quantities are like those that can be measured with like I don't know.
All right. So if you have notes, you can like go back on your notes. But Essentially, a vector quantity is something with magnitude and direction, right?
Yeah.
So a force can clearly have, so since the acceleration has a direction and it accelerates in the same way as the force, we can tell what the direction is of the force because we know the direction of the acceleration. So it is a vector because the acceleration gives us a direction, but the mass doesn't. So we're good. Okay. So I'm gonna say that it accelerates north for simple state. So that means it's a positive. So north is positive. Okay, so it's a positive answer. So it's 6600 newtons bracket north. But we're not done yet. We need to round this to two significant digits because we follow all the rules of physics. Right? So the two significant digits are well. Well, there's two significant digits, so we need to do it in scientific notation. So it'll be something times this times something newtons, and the two non-zeros we have are 6.6. So it's convenient to put that here. So these are our two sig digits, and now we need to get this quantity. So we'll multiply by 1, 2, 3. So 10 to the power of 3. So our final answer is 6.6 times 10 to the power of 3 newtons north. All right. So this question, although it looks simple, regular people, I mean, like some people might have not been able to do it because it has significant digits, it has scientific notation, it has a unit, and it has a direction. So, yeah, those are all things you need to look out for in physics. Okay, so we're gonna do an example. Wait, the break ends in 8 minutes. It auto ends. Okay, so I think it'll take about 8 minutes to explain this. But do you remember what the formula for acceleration was?
The what?
The formula for acceleration.
It is. Was it the final velocity minus the initial velocity divided by time?
Okay. Nice. All right. So this is my question, okay? And try it during the break because this is actually this is a much harder question than the one I just gave. So it is called, what is the force of friction of a ball that has a mass of 18 kilograms that comes to rest in 15 seconds from an initial speed of 3 meters per second. Okay, so some things. So we're just really quickly, the ball moves here, and the ball is moving here. That should be the only information I should give you. And the way the ball is moving, just define it as positive. So um okay, we should call this a direction. Okay, let's just call this, yeah, so it's moving west. Okay, so the ball is moving west. Okay, so based on that, right, you should be able to tell me what the force of friction is. You can define these directions either way you want. But why is this not moving? Hold on. Okay. All right. Well, that's a question. So run me through the auto ends in 6 minutes. Okay, so Rachel, when does it end now? 4 minutes. Okay. Okay. So, walk me through on how you would attempt to do this question.
Okay, so
Yeah, if you're stuck, you can ask, but I would at least want you to try and express how to do this. So, how do you think you would approach this issue? Hello? I don't really like the silence, but hello? Are you still on the call?
Here, let me try to give some guidance. I know it didn't work out earlier. You told me my bad. Okay. So looking at the question, you can start by listing out what you do know, like what's given in the question. What information are you given?
Right. So you are given, right, the mass of the object, 18 kilograms. You're given the final velocity comes to a rest, so that's 0 meters per second. You are also given the time, which is 15 seconds, and you're given the initial velocity, which is 3 meters per second. Okay, but keep in mind that the object is moving west, so it would be best to define this as positive. So I'll define west equals positive, east equals negative. So now that you have all this object, all what you have right now, your question is asking you what your force of friction is. Okay? So based on the 4 variables you have, based on the force of friction and this known formula of mass times acceleration, there's a pretty clear route on how to attempt this question. Okay, so the way you do it is you need to find the acceleration using these 3 variables, and then you multiply by the mass. But here's a prediction that I have to offer for you. So we know that friction goes against motion, and we know that the acceleration follows the force. So that tells us immediately that friction will be going east, so you will get a negative answer. So your answer will be stated with east on it because you already know that it will be a negative answer because that is simply the nature of friction, and that is how it works to say. Okay, so now let's analyze and solution this. Okay, so you have the formula, force equals mass times acceleration. All right, you know the formula for acceleration, so you can break that apart. Rachel, how much more time is left?
A few seconds.
All right, but now that I've given you this simplified formula, during the break, after the break, like the first thing you do, tell me the force of friction that you get, because you already have this formula.
Right.
All right, so can you please do that? Can you say like yes or no if you're gonna do it or not? Okay, well, we're back from the break, so do you mind telling me what you got for the force of friction?
so like you want to find the acceleration first?
No, so like, did you like figure it out during the break?
Sort of, I guess.
Okay, so what was the final answer?
Well, I got negative 3.6 Newton.
Okay, how would you say that in terms of the directions given?
Moving
Like 3.6 newtons, like what direction is it?
moving east.
Yeah, so don't say negative 3.6 newtons, say 3.6 newtons, and then say the direction, because it's more specific, and that way you actually you incorporate like a lot of skills that you use. Okay, but so this is the right answer. Yeah. So you just simply, it's a simple issue of plugging numbers in and then just solving it. 3 seconds. 15 meters per second. F equals 18 kilograms times negative 1/5 meters per second squared. And then negative 18/5 newtons, which is 3 3/5 newtons, which is negative 3.6 newtons, and since it's negative, you know that's going to go east. So the answer is 3.6 newtons east. Okay. So good job, you got the answer right. So we should be good for these simple force mass calculations. Kind of. Okay, so our next law is Newton's law is for every action, there is an opposite and equal reaction. So every time a force is applied to something, right? Like let's say you're walking and then your shoe touches the ground as you're like walking, right? The force that you use to touch the ground with, the ground then pushes the ground um also pushes the force upwards against your shoe. So equal and opposite mean, so these are equal. The magnitudes of the force are the same, but the directions are opposite direction. The directions are opposite. So like if you push the ground with 5 newtons, the ground supports your foot up with also 5 newtons. Okay? So this law is less studied, I would say, but there are applications to this law. So for example, if this law is true, right? You're probably asking, how does anything move then? So how do I use like for example, like well, there's probably a pencil case around you. How do you push the pencil case from here to here? How do you apply a force to it if the same force you apply here is the same force that gets applied back? Well, the simple way of explaining it is that, well, overall there's still more force. So even though your finger applies, at the direct like site of contact, there is a force, but overall there is a greater force on the thing that is pushing it. So like your arm and your body and your muscles, those all have external forces that add to push the pencil case forward. But if we're just looking at the pencil case and the finger, the forces are opposite and equal. Okay, so some questions you might get with this, well, you won't get them, but like some questions are like if there's 2 boxes, right? And then and then someone's pushing the box. Okay, well, there's a force that goes on this box, that goes on this box, and they're the same. So all of these forces add up. Okay, so these are just things in nature that are observed. So what are some examples of this in real life? Well, a gun. So a gun is really heavy. I mean, not really heavy, but a gun is quite heavy. Okay, and the reason why a gun is quite heavy is because you need to exert a significant amount of force. Well, not significant. You just need to exert like a lot of force to pull the trigger to set the gun off. So when you apply that force to the gun applies the same force back to you, right? But the formula, right, is mass times acceleration is force. So if both masses are the same, right, then the gun obviously has to be heavy, or else you'll accelerate. But okay, I think I'm explaining this very badly. I remember there was an explanation for this, but right now I'm a little brain dead. Rachel, can you help me out here?
To explain.
Okay, so to explain why a gun is so heavy.
Why a gun is so
Because
heavy?
a gun is heavy because like when you use the gun, you exert a force and the force exerts back to you. But like it has something to do with like since the gun is heavy, it won't accelerate or something like that.
Oh, rebound. Right? Is
Yeah,
that
can you like quickly explain that?
okay? Angel, I'm just gonna quickly ask you. You're familiar with rebound, right? So when you like shoot a gun and like it exerts a force back against you. Do you know what that is?
Um,
They show it in films, but I don't know if you know it.
sort of heard about it, I think.
All right, basically, okay, I'm doing a
Go,
little
Tony.
bit of
Go, Tony.
research, but a gun. So like, if you shoot a gun, right? This is a force, right? Now there has to be a backwards force, right? So the backwards force comes back to you directly, right? But if the gun was like really light, right? So let's say this has a force, right? And this also has a force, right? So when it comes back to you, when it shoots, like when the gun like recoils back to you, like when it goes, like when it comes hurtling towards you when you're holding it, if the gun was really light, the gun would like accelerate towards you at like such a fast rate, and it would hurt. So they make guns heavy so that the gun does not affect your movement that like it does not affect your movement that much because if the gun was really so the formula is MA, right? So M M it's like this, right? Hold up. Yeah, so it's mass times acceleration with mass times acceleration, right? So well the mass of your hand that you use to fire it accelerates the gun a lot, right? Because the bullet clearly accelerates a lot. But when the gun recoils back to you, you best hope the acceleration is not a lot, or else you'll get hurt. So that's why they make guns heavy, because as you increase the mass, the acceleration decreases. So this inverse proportion allows you not to get hurt because the gun does not fire back and hit you. It fires back at you, right? That happens, but it's not that much because guns are heavy. Okay, does that sort of make sense? You can type in the chat. Does that sort of make sense to what I'm saying? Yeah. Okay. So another way you can think of it is like a rocket ship, right? A rocket ship. If the fuel that's burning out of it, right, is a action, and then the reaction is that is that like is that there is another force that propels it forward. So this is what makes a rocket go forward. It's that when you release the fuel, right? The fuel exerts a force back on the rocket, and this motion propels the rocket to go forward, to go up. So fuel out, fuel exerts force back on rocket, rocket goes up. Okay, action reaction, right? Yeah, basically that's it. I need to watch this Newton through London video. This is actually interesting. I'm gonna do some a little research on it. Okay, so the next thing. So those were Newton's three laws, but I do have a trick. I have a question with this. Okay, so so let's say so there's a scroll, right? There's a little keep in mind this analogy is not the best, but it's a pretty decent analogy. So there's a scroll and it's sliding off a rooftop, right? No, wow, that was a horrible scroll. Okay, so there's a scroll and it's sliding off the rooftop, right? and it has like a lot of nuts on itself, right? So if the squirrel, being as smart as the squirrel is, if the squirrel knows what Newton's third law is, what does a squirrel do to save its life from an angry like dog or something over here? So you can unmute your mic when you say this. But what do you think the squirrel does while it's sliding off the roof? While it's sliding off the roof and it's about to get eaten by a dog, but it has a handful of nuts. What do you think it can do to save itself? Knowing that it knows Newton's third law, what do you think it can do? Can you unmute your mic, or is that difficult at this time? Okay, so you unmuted your mic. So what do you think can happen? What do you think the squirrel can do to save his life? So it's okay to say I don't know. Okay, normalize saying I don't know.
I don't know.
Okay. Okay. So okay. So if the squirrel throws the nuts back here, the force a force that's exerted on the nuts, right? And then then an opposite and equal reaction will happen back. So then the nuts will exert a force on the squirrel, right? So it throws this force that the nuts exert back on the squirrel can help slow down its sliding off the roof because it's pushing it backwards. So it throws its nuts, the nuts quote unquote throw back at the squirrel, and the squirrel slows down, so it is safe from getting eaten by a dog. So yeah, Newton's third law. Opposite force has an equal and opposite reaction. Cool. Okay. So now we're gonna do work and energy. Okay. All right. So the definition of energy is a quantity which needs to be transferred in order to do work and all other actions. So now you're probably like hella confused. You're like, wait, this is weird. What do you mean you need to do work? What is even work? Well, first, so energy is basically this property, like this property that all things have, and this property of things, it can be transferred into multiple forms, so we can do things, we can get things done, we can do work. Your food, right? When you eat food, we eat food so we can get energy. We eat food so we can be able to like so we can I'm yawning, sorry. So we can run and stay strong, and these are all energy because you need energy to perform all these actions. So yeah, and energy in the body comes from ATP. It's like this chemical, and it's used to perform the functions of cells. But that's getting too far. We're entering biology territory, but yeah, so that's energy in the body. So let's define work then. So work describes a change of energy that occurs when an object moves 1 meter along 1 Newton of force. So first, let's have work is a change of energy. So why is work a change of energy? Okay, so energy is the ability to do work. Okay, we need energy, the quantity energy to move things. Okay, so when we utilize the energy, in an object and it moves, right, or it changes, or something happened to it, that shows work because the object is moving, right? So, okay, wait, maybe I think I explained this. I think I explained this wrong series of events, but let's explain this part first. 1 meter along 1 Newton of force. Okay, so work is 1 meter along 1 Newton of force. So the object travels 1 meter along 1 newtons of force. So I apply 1 newton of force, it moves 1 meter, and that is 1 work. Okay, but the unit for work is joules. 1 joules. So joules equals newton meter. Because the formula, right, for work is this. Work is force times distance. Okay, so work is force times distance, and it's measured in joules, and a joule is equal to a newton meter. And this should, and now we will explain why work is a change of energy. Okay, so energy is within things, within objects, within quantities, right? So in order for the energy to, in order for the, in order for an object to move, which is defined as work, like work, an object has to move during work, okay? So when an object moves, right, we need to utilize the energy that is there and turn it into something that can allow the object or whatever to move. Okay, so that is why energy is work is a change of energy, because it changes the format of energy that is stored into something that is now moving, or to something that is now now useful. Okay, let's just say useful. But here's the thing, right? Energy has the energy's units are also joules. Okay, so energy has the energies. Why am I stuttering? This is not okay. Okay, but anyways, energy's units are joules, and they're the same as work. So why are they the same? Well, obviously, if you use one thing to do another, right, they should be the same. It's like you need. It's like I don't know. I always think of it as like if you need like energy like paint, and if you paint a room, it'll be the same color as the paint. So that doesn't really make sense. I have weird ways of thinking of things, but that's just that's an observation. Okay, so now we know what work is. We know what energy is, right? We need to describe some types of energy because it's in the curriculum. So we're going to go over some types of energy. Okay, so electrical energy. What do you think electrical energy is? I'll just go over it. So electrical energy. Wait, no, I'm doing this in the wrong series of events. So first, there's 2 categories of energy. Okay, there is mechanical. I mean, there is kinetic energy, and there is potential energy. So potential energy are things that are moving. Okay, things that move have kinetic energy. Things that are stored have potential energy. So the energy is there, but you need to use it. Okay, so that's similar to the relation between work and energy. The energy is there, but you just need to use it and change the form so that you can actually start letting things move and start getting work done. Okay, does that sort of make? Okay, I need to check in with you. Does that what I'm saying sort of make sense? You can unmute yourself. Yeah, just next time if you can just unmute yourself, because like yeah, nothing's wrong with unmuting yourself. So there's 2 types of energy. So there are kinetic energy, which is moving, and potential, which are stored. And we and we will go over some types of each energy, so you actually know in the curriculum. Okay. So thermal energy. I mean, no. Let's just start from electrical energy. So electrical energy is energy stored in electrons or like electricity. So when electrons are just like vibing by themselves, they but no, I mean sorry, when electrons are moving, through a circuit and they're powering up your house, that's electrical energy. The electrons are moving to do work, okay? And then there are things like thermal energy, heat. So heat is also a type of energy that moves because the heat, the particles are the particles that are being heated up are moving because the temperature increases. So the more movement increases, like that's a particle model. Particle model. Rachel, I'm lost for words right now. What was that model called again? Particle model of matter or something?
Yeah, particle model of matter.
Yeah. So when something's heated up, so when you heat up something, it moves because that's just the way things are. Okay. Sometimes in science, the answer is that it is what it is, right? So those are things that I would say that are kinetics and stored energy, right? We have things like chemical energy, right? So chemical energy, the bonds between chemicals. So right, so there's a lot of energy between the bonds of chemicals, but they have not been utilized yet. But once you bond them, they might release energy. So that's why it's stored. And other things that are stored are gravitational energy. So gravitational energy is an object that is held at a height or held at some point above the ground, where if dropped, it can release a lot of energy. So that's why it's potential. It's stored. Nothing's happened to it yet, but something could happen to it because you have the potential, right? Get it? Potential of releasing energy by dropping it. Okay, so those are just examples. And then nuclear energy. I'm pretty sure how a nuclear bomb works is that a new like a element splits into two and it releases a lot of energy. So right, it's not released yet, but it could be released. That's why it's potential. Okay, and also in kinetic, there's like sound energy. So you can make sound to disturb a number of things, and it can generate energy for the community. So these are the things. These are the forms of energy. Um, so there's actually another type of energy called mechanical energy, and mechanical energy is the sum of uh. So EM is a sum of potential energy and kinetic energy of any given time in an object's motion or like yeah, not really motion, but like what happens to it. So usually in Science 10, we deal with these type of problems in the simplest ways possible. So in Science 10, we learned that the formula for gravitational potential energy is mgh. Okay, so mgh. So I never went over weight. Oh, 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 darn. Okay, so let me just go over this real quick. Crap. Okay, so on Earth, right? Do you know why things fall? Because of gravity, right? Because there is a force that is directing us towards the center of the Earth, and that is called the force of gravity, right? And the force that directs you towards the Earth always has the same acceleration, everyone on Earth, right? That is a gravitational constant, right? That is negative 9.81 meters per second squared. This number is important. So the negative means it's going down, but 9.81 meters second squared is fine, but you just have to put in brackets down. But this is the acceleration due to gravity, okay? And this acceleration this is the rate of acceleration that drives something towards the Earth's center, like towards the Earth, right? So I'm gonna take a pencil and I drop it. That's because there is a constant. That says there is a constant acceleration moving everyone down, so we are close to the Earth's center. Okay. So now, how does that relate to the force that's pushing you down? Well, the force that's pushing you down is called weight. weight is not how much you weigh. Like weight in physics is not your mass. It is what is a gravitational force pulling you down. So we know that force is mass equals time acceleration, right? And we know this is g, and this is the unit for acceleration. So that means weight is your mass times your gravitational constant, right? So that means weight equals mg, simplified formula. So that is the amount of force that is pushing you down at all times. Okay? So this is just a concept of weight. Does that make sense? Like, do you understand this concept of weight? It's just what is the force of gravity pushing you down? Do you understand? Hello? Do you kind of know what I'm saying? It's just because gravity is a constant acceleration that pushes you towards the earth. Okay, yeah, you understand. Okay. So if we go back to this formula, right? Why is it mgh? Well, you have a force that's pushing you down, right? Like there's a force, there's always a force, so that force is gonna act upon you when it's in the air. But then at the same time, right? Your height. This represents height. So the height of your object towards the ground is this variable called height. Okay. And this variable called height fits well with this formula because if something was to be dropped, well, the energy that would be released, right, would be like, So work is force times distance, right? So this has a force and this has a distance. So this is the amount of work it would do if it was released. So that's why this formula made sense for gravitational potential energy. For something that is in the air and could be dropped at any moment, that was the formula to calculate the energy of it. Okay? Okay. So then the formula we have for kinetic energy is mv squared over 2. We have no clue how it's derived because school doesn't work like that. But this is the formula. So v is the speed that you are moving at. And you multiply by the mass and you divide it by 2. So then you can find your kinetic energy. And that is a summary of mechanical energy. So an example of when this would be used is if there's an object at a cliff and it drops down. At any given point, there is the height, so you can figure out the potential energy. And then there's also a speed because it's moving, right? Because you're throwing it, so it has to move. So then you can find out the kinetic energy, right? But in Science 10, right, it states that the mechanical energy, all right, it stays constant throughout the object's motion. Okay, so why is it unrealistic? Well, in real life, energy does not stay constant because energy will be converted to something that cannot be used back, like friction, right? Or like sound, or like heat. All of these energy conversions cannot be converted back into usable energy. So that is why. So that is exactly why your energy cannot stay constant at all times. But in this ideal world of Science 10, your energy can stay constant at all times. So if at any time, right, the mechanical energy is the same, right, when you drop it, right, well then you can tell when there's going to be the most potential and the most kinetic and the most kinetic and the least potential. Okay, so we're going to go over that really quickly. Wait, do you have to go at 5? Or wait a minute.
Tony, just estimate how long you'll take and then ask Angel if she's available for that. period of time? Like how much?
How long is the meeting over?
The meeting will auto end in 7 minutes, but the lesson should be over right now.
Okay, well, if she has 7 minutes, we could go over just like the last final touches of physics 10.
Sure. Angela, is that okay with you?
It's her choice, though.
Overtime? All right. She's good.
Sure. Okay. So if mechanical energy stays constant, right, and you're dropping an object down to the ground, well, you can tell when it has the most potential and the most kinetic. So when it's at the top, right, your object is not moving because you have not dropped it yet. So it's not moving. You're holding it in your hand. It's not moving. So that means EM equals EP plus EK, right? Your speed is 0, right? So look at this formula. Speed is 0. So this is cancel out. So right now your EM is equal to your EP. So you're given the height. If you're given the height of the cliff and the mass of the object, you can find the total mechanical energy just by that. All right. So just by that, you can figure out the mechanical energy of it. So now let's review a case at the bottom. So at the bottom, right, there is no height at the very bottom when you drop this. So there's no height. There's no gravitational potential energy. So so EM equals EP plus EK. So we'll cancel EP out. So it'll be EM equals EK. So now the question that people like to ask here is, well, what is the speed of the object at the very bottom? Well, you can calculate that by doing mv squared over 2 equal to EM. But we don't know what EM is. But remember that we just established in the previous example that EM equals EP at its tallest times. So then you did this formula, mgh equals mv squared over 2. Okay, well, that makes sense. So now you want to find speed. Well, this is pretty easy now. So you cancel out the h, so they're on both sides. So now that we cancel out the h, right, we know one of two things. This is 2. Oh my, I'm so used to writing the physics like 20 uniform circular motion formula. I wrote that instead. My bad. Okay, but now that the h's are canceled out, we know two things, right? If we are given the height of something, right, we do not need the mass of it to find the speed of it. Okay, because the speed of it will simplify into v equals 2gh square root, the square root of v 2gh. That would be the speed of the object when traveling down. Because we determined that through two different cases. So the case up here is speed is 0. So case up here, EM equals EP. The case up here, EM equals EK. Well, EK is constant. So EK equals EP, which equals mgh equals mv squared over 2, which equals v equals square root of 2gh. So that was a long formula, but this formula is useful because most of the examples regarding mechanical energy like this formula is like pretty much just a shortcut on how to do it. So this formula only applies for a bottom of motion where height is 0, where h is 0, and then quote, and h is tallest. H is the tallest height in the question. Okay. Rachel, how long is the meeting? How long?
You have 3 minutes.
3 minutes. Okay, that's actually not. That's. But I didn't go over words one more time. But yeah, that's it.
You can wrap it up
Huh?
next lesson. You can cut into my bio.
Okay. But anyways, work is force times this displacement. But there are conditions for this work. So the work means. So in this specific problem, right, work and force and distance, they actually have to be parallel. So if your force is going this way, your distance best be going this way. So only when the force and distance are parallel, right? Then you can calculate your work. Okay? If your force is up here, right? You have to do trig to find out what this component is to figure out how much you move from here to figure out the work. Okay? So that's just a key note about work. Another thing about work is that work is a scalar value. So work is scalar because it cancels out two of the same directions. So work cancels out the direction of force and the direction of displacement. So because it cancels these two things out, it becomes a scalar quantity where there's no direction of work. But then they go on to say that, however, you can still encounter negative work, okay? When they ask you for the work of friction, right, it's force of friction times displacement. Well, force of friction is negative because it moves opposite and displacement is positive. So your work of friction is going to be negative. It's going to be some negative. Okay? It's going to be negative. So although it's technically scalar, you can still encounter negative work if they ask you for friction. But that's just like in a special case in
Yeah,
general.
you have like 30 seconds.
I have 30 seconds. Okay.
Yeah.
Well, this is basically we finished physics throughout the 4 classes that we had. Basically, it's all covered, but we didn't really do any examples for these. So if there is time next week, we might do it. But if there's not, we won't. But yeah, EM equals EP plus EK. Work equals force times distance. Force equals mass times acceleration. I just summarized all the entire unit for you. But yeah. So have a good weekend.
Enjoy your math class. Oh, I should end the recording. Oopsie.